We'll now look at how angles and circles can be related. And we'll start with what's called arc length. Here's our basic setup. We have this circle and we have two different angles. And we're going to look at the length of the arc that they intersect. In this case, angle theta intersects an arc of length s. Theta prime intersects an arc of length s prime. And so since we've defined these radians nicely, we should actually be able to set up a ratio because these are essentially similar triangles. We have theta over theta prime should be equal to s over s prime. Well, we know that if one of our angles is 1, the corresponding arc length is equal to the radius. So this tells us that the angle times the radius is actually equal to the arc length. So now we have a way of finding arc length using this formula. Let's consider this angle of 1 over 6 radians and a circle of 7 inches, and we want to know the corresponding arc length. Well, the formula said s is equal to r theta. So we would just do 7 times 1 over 6 to get that the corresponding arc length is 7/6 of an inch. This time, we know the arc length is 9 inches and the corresponding angle is 30 degrees, and we want to find the radius of the circle. We can still use the same formula, however, it's very important to note that theta must be in terms of radians. So we'll start by multiplying 30 times pi over 180 to get pi over 6. I know my arc length and I know my angle. We can then take each side and multiply by 6 over pi. On the left, we get 54 over pi, and on the right, we get r. And this is going to be the exact value of the radius. However, we can also reduce that and approximate with 1.79 is the approximate radius. This time, we know our arc length is 12.5. And we know our radius is 4, and we're trying to find the corresponding angle. We can divide both sides by 4. And then we have that 12.5 divided by 4 gives us an angle of 3.125 radians. Next, we'll look at an angle in a circle and its corresponding area of the sector that it carves out. This will be set up originally like arc length. If we know that angle theta corresponds to an area of A and an angle of theta prime corresponds to an area of A prime. Essentially, we're going to eventually want to know A. So multiplying by A prime tells me A prime of theta over theta prime. This should work for all angles. Therefore, if I let theta prime be 2 pi, the entire circle, well, A prime would be pi r squared since it is the entire circle, and we know how to find that area. Reducing then gives us 1/2 pi r squared theta for the area of the sector. Here we have a radius of 4 feet and an angle of 60 degrees. And it's important to note once again that our angle needs to be in terms of radians. So multiplying by pi over 180 gives us pi over 3 radians. And now we can use our formula. We have 1/2, should be a pi in there, pi r, which is 4, squared times theta, which we just found to be pi over 3. And now we just need to reduce this. 4 squared is 16, divided by 2 is 8. So now I have 8 pi times pi over 3. And now we can just reduce this to approximate the area. We have 8 times pi times the second pi divided by 3, which gives us that the area is approximately 26.32 square feet. This time, we know the area and the angle, and we want to find the appropriate radius. My area is 16. I don't know my radius, but I do know my angle. So we'll start by going ahead and multiplying out the right-hand side, which we have 1/2 times pi divided by 2, and that's approximately 2.5 r squared. We then need to divide 16 by that number. So we'll divide both sides by this 2.5. When we do that, we get approximately 6.5 is r squared. And then taking the square root gives us a radius of approximately 2.5 feet. This time, we know the radius in the area, and we want to find the appropriate angle. So our area is 6, and we know the radius is 12. On the right, we have 1/2 times pi times 144, which gives us approximately 226.2 theta. We can then divide by this number on both sides, and that gives us that our angle is approximately 0.027 radians. We'll now discuss the speed around if you are moving in a circle. And there are two ways to define speed. The first is linear, which essentially means if you stopped going in a circle, how fast would you be going? It's essentially the way we think of speed now. We will have 3 variables. R is the radius of the circle that we're moving in. S is the distance around the circle that we have moved during time t. And then in this case, our linear speed, v, is the distance divided by the time. Ultimately, our radius is not going to be super important in this step. We also have angular speed. Angular speed is essentially how quickly you're moving in a circle. How many circles do you make in a given amount of time? In order to find our angular speed, we need to know how long it took us to get through a certain amount of angle of the circle. So essentially, if we've traveled a certain angle in our circle, then how long did it take? In this case, our angular speed, which is given by omega, is our angle divided by our time. And we can actually relate these two ideas. So this was our linear speed, and S is just r theta. That's our arc length. So this is r times theta over t, which is r omega. So we have that v is equal to r omega. Let's consider the Earth and the Sun. The average distance from the Earth to the Sun is 9.29 times 10 to the 7th miles. To simplify this, we're going to assume that the Earth has a circular orbit and find the linear speed. We know that v is equal to r omega. And we know the radius because the Sun is at the center and we know how far we are from the center. For omega, we have to consider our angular speed, which was theta over t. If we go around the full circle, it takes us 365 days. So that would be our omega. So now we just need to multiply this out. And when we do, we get that it is approximately 1.6 times 10 to the 6th. This is miles, and our angular speed was given in days. So the Earth travels 1.6 times 10 to the 6th miles every day. This is our speed.